Welcome everyone to another meeting of the Berlin Functional Programming Group Zoom edition. Today, I am delighted to introduce my friend Alejandro Serrano Mena. Alejandro is the author of two books, one of which is very close to my heart, the other of which I haven't read, but I know that it exists, Practical Haskell. I don't know how he feels about Practical Haskell, but the Book of Monads, I hope he feels very highly of, because it's a book that I got to participate in the making of. I got to edit this along with Alejandro, and it was a great experience. It's a great book. I highly recommend it. Alejandro is not just an exceptionally intelligent functional programmer and an asset to our community, but he is a generous and gregarious and friendly guy, and we could use as many such people as we can get in the functional programming world, in my opinion. He used to be an academic, but like me, he has sold out and joined the corporate world and is currently working, I think very happily from what I understand, for 47 degrees.
Indeed.
And actually gets to do some work in training and open source on Haskell. So actually doing work on behalf of the community, which is extremely valuable. And I'm extremely jealous of you as well for being able to do that. It's really wonderful. And it's wonderful to have you, Alejandro. I'm really looking forward to your talk. You always present concepts in a way that people who don't necessarily have advanced exposure to FP concepts and to Haskell can understand. And this kind of outreach is especially meaningful to me. I think I always like to say that if we're lucky, most future Haskell programmers don't exist yet, right? We want to create more Haskell programmers. We want more people to become acquainted with functional programming concepts. So please take it away. Everyone, please enjoy our talk with Alejandro Serrano Mena.
Yeah, so thanks, Steve. I mean, I think, yeah, I'm blushing. So I should stop here and just go away, something like this. But, well, first of all, let me try to see whether, I guess everybody should be now seeing the title of the talk, in which indeed I'm gonna try to talk about some concepts and some more abstract concepts like functors and monads and so on. So let me start. So of course, welcome everybody. We've seen there's people from all around the world, which is, great. Even for me, I mean, I would really like to be able to go to Berlin and then to London and everything, and actually having this kind of virtual meetups is a way for everybody to come together when, sometimes it's not that you are that far, but already a couple of hours by train is something you cannot do on a daily basis. So, well, anyway, welcome. And just to give you a brief introduction of what the talk is about. So the questions I would like to answer with this talk is, why do we need things like monad transformers, which you might have heard or you might have used, but there is no something like a functor transformer. Why this does not exist, and also why it's so complex. What is so complex about combining monads? It's like everybody seems to be wanting to combine monads and inventing things, and why is that hard? Why can't you just put them together and they'll be friends and they will work together? And on the way, we're going to learn about a few other things. We need to understand this. So in general, what is functor composition, and something which is called the monoidal presentation of applicatives and monads, and also some tricky bits of Haskell typelets. We need to understand this. But just so everybody doesn't run away right now, everything is going to be mostly in an intuitive sense, which means that hopefully you will understand more. But maybe you won't be able to just copy the code right away to your code, because I will be stripping some details, and I will tell you what details I'm stripping out. But I need to do this so we can concentrate on the important stuff. So anyway, I mean, I've already been introduced by Steve, so thanks for that. As I said, I work as a trainer and software engineer 47. Before I was a lecturer at Utrecht, where I live. And I wrote a couple of books. So, Book of Monads, it's a great book if you want to understand this kind of stuff. And actually, it's great that it's a book that which I collaborated with a lot of people. So Steve did a great job on checking all the text, but other people have been checking all the snippets of code, trying to ensure that everything can be well understood. So it's a great sort of community thing, even though my name is on top. And then I also wrote Practical Haskell, which is like a book I wrote because I felt like there was, at the point when I wrote it, there were several beginner books for Haskell, but there was this missing link. So, okay, I know to use Haskell, but how do we do databases? How do we do web services? How do I use parser combinators? And these kind of things are in Practical Haskell. So, if you want to have a look, it's a great book. Now that I have nothing to do with it. So. But anyway, let's go to the talk. So first of all, I've been talking about composition, and maybe I should be a bit more clear what I mean by composition. And in general, when we talk about composition in sort of the functional programming world, we tend to think about some way of combining two elements to obtain a third one. And the kind of things we combine are of the same kind, and then we get yet another thing of the same kind. So for example, you have function composition. You take two functions, f of type AB, g of type BC. I actually mixed the types there, but well, kind of the point is the same. And then you get yet another function. And this is actually a case where not every composition is allowed. So composition doesn't mean that you can always combine stuff. There are some times where you cannot combine stuff. So in the case of a function, the types have to match. And then you have other kind of composition like monoids. So actually nowadays you have to use semi-group in Haskell. So, and the semi-group composition, which we call like, angle bracket, close angle bracket. So you have to think, people call it like a diamond. You can just compose any two M's and get yet another one. So the point is always you get two things and then you get another one, and the one you get is of the same kind as the second thing, where kind and of the same are all these kind of wavy kind of thinking. So sometimes they're functions, monoids. So what we are going to do is we're going to try to do function composition. Right before that, let me just, so that everybody tell you what I understand about all these functor applicative monads. So this is the general summary of what you have. So functor is a type class. So it's something we say about a type. So like list is a functor, or maybe is a functor. And if you're a functor, that means that you have a function fmap in which you can, again, being very wavy, apply within a context. So you have a function and a list, and you can apply the function to the list. Or you have an optional value and a function, and you can apply the function to the optional value. That's what functor tells us. Applicative get us one step farther, because you cannot only apply within a context. You get two new superpowers. You can get something which is pure and put it inside of the context. So like you have one element and you put it inside a list or inside a maybe, and you can also sort of combine independent computations. And it's a bit hard to see it from the type of this operator, which I will call up. But the idea is you have two computations, you can combine them somehow. And if you have applicative, also something you can do is get several independent things and combine them using a pure function. So that's what you get from applicative. And then a monad is something which builds even higher, in which you can have a dependent computation. So if you look at the type there of the very last line, that's like reverse bind. So that's like the operation you have in monad, but I just swap the arguments so you can see more clearly that they all have the same kind of structure. So you have now an f of a, so that's like something in a context, and you can apply a computation, but this computation f of b depends on the a. So that's like the power you have. So functor is just a way to apply one pure function. Applicative gets you a way to have independent computation being combined, and monad gives you dependent computations. That's kind of the very broad general summary of what all of these do. So what we want to do again is compose two functors. So I want to, you give me two functors, I give you another functor back. And before we dive into the general stuff, what we can maybe do is just look at some examples. So let's think we have a list of lists. So that's the composition of two functors, the list functor and the list functor again. So we have a list of A, which is like one iteration of the list wrapped in another list. So that's like the composition of list and list. So what does fmap means in that case? Well, it means that you have a function like this list I have there. So you have this pure function A to B, and then you have something of the type list of A. So that's the composition of the list within the list. And then you want to get something of the same functor, which is list, but with B's. How do you do this? So if you kind of think for a while, what you get is something like, okay, I map, and inside of map, I apply map. So it's like I iterate over the outer list, and whether within the outer list, I have also lists. So I apply the mapping operation within each of the inner lists. So that's how this fmap for list works, which I can write like in the left, like map applied to map of f and x's, or I can drop the x's in both sides and I get map with map f as an argument. And something important just to be careful with this is that I'm not applying map after map, which would be what I have in the not this thing. So I'm not getting the x's and applying the f and then the result applying it again, which we could also write like map composed with map f. What we are doing is applying map, and the argument of map is itself a map, which is slightly different from applying map twice. So what you get from the first is you get the map f applied to each element of the list, and the inner map f applies to each element of each inner list. So that's how you get like this kind of nested list computation. So now let's imagine we have something like list of maybe. Well, we can write something very similar. We get map to go into the outer list, and then within the inner and then within the elements of the list are maybes. So we can use fmap, which is the generic functor application, to apply f inside of each maybe. So that's how we do it. So map, and as an argument to map, we have fmap. So maybe you can already spot the pattern, which is if I have two functors, f and g, and I want to get this sort of composition of the fmap. So I have f of g of a, and these f of g are going to be in general functors. I can just apply fmap, apply to the, with the first argument being fmap of f. So it's like you get the outer f, you get the first layer with the first fmap, and then inside of the f's, then you have to apply the fmap of g. So it's like you go each step, and you can actually think of doing this in general with 4, and then you get fmap of fmap of fmap of fmap of f. That's how you do this. So this type checks, this work is suspected. So actually, if you apply fmap2 to a list of lists, that's what it should do. And if you do it with a list of maybes, that's what it should do. And if you apply with a state s of list of reader t, which are all functors, this works perfectly. So no transformers, this is your normal functors. We can compose them and get a new functor in return. Now, what about, writing not like a function which does what we want to do, but actually writing the functor instance. So writing, being able to treat f of g as a functor and just write one single fmap for this, which would do the nested fmap. Well, it gets a bit hairy there. So what you need to know at this point is that type classes in Haskell cannot have whatever you want in the head. In particular, you must start all with a type constructor, which means that things like instance, functor, list are okay, because list is a type constructor, it's a concrete type, if you want to think about it. Instance functor maybe is okay because it's for the concrete type constructor maybe. But if we want to write what we had before, we want to write something like this. So this is all not Haskell, but that's sort of what we want to write. So we want to say, if we have an instance of functor for f and an instance of functor for g, we have an instance for f applied to g, but the problem is that we cannot drop type arguments as we do with construct. This F and G you cannot really drop as you did maybe of A. You cannot drop this A to get maybe in this case because things are nested. So I think in Scala you can do kind of things like this, but in Haskell it's forbidden. And the second problem is that this instance is not headed by a constructor. So this functor started with an F, and this F is a type variable, not a concrete type. It's something which can vary in compile time. So why you cannot have this? It's a kind of a bit technical, but if you don't have it, you get a system which doesn't work as nice as you want. These rules are in general called the patterns on conditions. You can check about it. You can ask me later if you want. But this is something you just cannot do in current Haskell. You really need to be headed with a functor. So the trick is to have a wrapper type. So we introduce this compose type. So this compose type is just something which wraps a single field, which is of type f of g of a. So just for people which might not be completely used to reading Haskell data type, this means that we are defining one data type called compose. This compose has 3 type arguments, what you would write in angle brackets in Java or in Kotlin or in a square brackets in Scala. And it has one constructor, which is also called compose, and has one field. And this field has type f of g of a. It's like we are wrapping what we have inside of these single field, single constructor data type. And why we use new type is also because, well, this new type is a special thing in Haskell, which has 0 runtime cost. Not that it matters here. What matters is that now we can express something like a composition of maybe and of list and maybe using this compose. So whereas before we had list of maybe of integer, we now write compose of list of maybe. So this composes the 2 functors and then applies it to integer. So what you have here inside is actually going to be a list, because that's the F, of maybes, which is the G, of integers, which is the A. And if you see, I have exactly that. So I have a list and things are like just one or nothing are maybes. And then we need this extra constructor called compose to have not something of type list, but something of type compose. And if we do that, we won't, because now we can write the instance, because now compose is a data type. So we can write functor of compose fg. We drop the A as we usually do in functor instances, and then we can write something like this. So the fmap of compose is going to be the sort of nested fmap, but we need to remember to unwrap the compose to expose the inner field and to wrap it at the end to get the compose at the end. So I know what you're thinking. It's like the adapter patterns, you need like OO vibes here. So, you have to create an adapter data type to be able to do the instance. It's kind of a trick you have to play sometimes here. So if you have this, then you can do it. But keeping track of this constructor is, first of all, utterly boring, and it's super distracting for what we have to do, because once this gets harder, we are gonna see what we wanna do, and then we're gonna have composes all around the screen. So because we don't want to have that, I'm just gonna show functions like this, like fmap2, like I was showing before. Instead of the actual instances, you can always get the instances by spilling enough composes here and there. So that's that, if you have some time these days, try to get my code and put enough composes for it to type check. But anyway, so you might be asking, if you've been doing some Haskell reading, functors. We are always sort of very we tell all the time, functors also must satisfy laws, that you can just get anything which type checks. Functors also satisfy laws, and these are the laws of the functors. Good news is that what I've done just respects the laws. Sometimes are easy to check. So one law is that if you map the identity, you get the identity. And you can actually prove this like in 3 lines that I've done here. So because you have fmap of fmap ID, the inner fmap ID is ID, and then applying the rule again for the outer functor, that means that this is ID. So this works. And the composition law takes a bit longer, but it also works. So, you know, everything actually works. So functors can be composed. I can give you two functors. You give me two functors, I give you a new one. This is actually a functor, not only have an F map, but every single law of the functors is respected. So, you know, functor composition works. You take list, you take maybe, together. Now, what about something, so the next step on the ladder, what about applicatives? So applicative, as if you remember, had these two operations, pure and app. So in this case, this is the type of pure. So it gets an A and gives you back an F of A. And, you know, we want to get one for the composition. So that's like, you get an A and then you have to do F of G of A, because this is like the two composed functors. So now I want to try something which I said I've been heard that works, which is doing fancy drawings on the screen. So let me try to actually make it work. Let's see if it works. So I hope you see nothing right now. You know, Steve, can you? Well, hopefully you see me writing sort of pure right now.
Yep, I see it.
Yeah, good. So as I said, we had pure. It has this A to F of A, and we have the same pure but for G. So it has A to G of A, and we want to write a new pure 2 which takes the A to the F of G of A. So that's what we want. So what can we do? Well, we can take some A, so that's some X of type A. Then we apply pure. Which pure? We apply the pure for G, so we get G of A. And if we now apply pure to this result, so now we apply the pure for F, we get F of G of A. So that's how we can easily do this. So we get the first thing, we inject it into the inner functor, then we inject this result into the outer functor. So that's how we get two pures. So let's get back to the slides. So that's what we have. So pure 2, it's pure composed with pure. That's how it works. So good. Hopefully pure is okay. Let me stop here before we dive into the harder app. So are there any questions? I think Steve was looking at the chat window. So are there any questions about like the functor or pure part that we could maybe solve now?
I don't see any questions in the chat, but I invite people to drop some in.
Yeah, if you have questions along the way, we'll try to make sort of stops here every time there is a new concept, so you can ask questions. So okay, let's keep on that. So that's app. So that's how you do app. If you have app of two things, you can write this thing, which maybe for you it works, but all I see here is, you know, like the greatest operator soup in Haskell. So I have like thing in parentheses with stars applied with dollars and stars. So this doesn't give, I mean, I don't have a clue of what is going. I can see it works. You know, the compiler tells me, okay. And if I apply the thing, it sort of works. But we would like to do it in such a way that, you know, it's intuitive how we're doing this. So as I said, to do this, we're gonna look at the monoidal version of applicative, or if what we would see for applicative is something which respects tuples. So this is how I'm gonna write the new applicative class. So I still have pure, but instead of app, I'm gonna have this AND operation, which takes f of A and f of B and turns this into f of the tuple of A and B. So this is the operation we're gonna have instead of app. So you can think of like, if you have two maybe of A and maybe of B, if both of them are just, it gets the tuple. Otherwise it gets nothing. If you have a list of A's and a list of B's, it gets the Cartesian product. So all combinations of A's and B's. So that's how this will do. But maybe if you don't see how this is tuple respecting, maybe what we can do is apply and carry, which essentially means instead of taking one argument at a time, so instead of having and taking f of A and then f of B and then returning f of the tuple, if we put these two things together, maybe you can see that everything which AND is doing is moving tuples inside the function. So we have a tuple of fa and f of b, and now we have an f of a tuple of a and b. So this is like the tuple is going from the outside to the inside. And we're gonna see, we are gonna play this kind of games in which we have something outside and put it inside and so on several times in this talk. So the technical term of this is being a lax monoidal functor. So if you wanna search and wrap your head about this kind of categorical names, actually just as a historical side note, the original paper which introduced applicatives in Haskell, which is called Applicative Programming with Effects by Conor McBride, and the same Patterson of the Patterson conditions, introduced both the normal, what we see now as the common presentation, and this sort of monoidal presentation. And they thought that that would be, I guess, equally interesting, but the time has shown that the first one, so the one with app, seems to be much nicer to work with, and this other one is kind of less known. But just so you know, just so you don't have to trust me on this, I'm going to show you that these two things are really the same, which means can we express and in terms of app and functor, because we always have functor there. So just a small note, this dollar in brackets is also fmap. So that's if you use applicative notation, you sometimes use this other version of fmap, but that's the same fmap. So the question is, can we express one in terms of the other and the other in the terms of the first one? And the answer is yes. So we can apply and like this. So this is sort of applying the tuppling operation to two arguments, f of a and f of b. And we can also do it vice versa. So we can, if you want to apply f of a, which is sort of taking an f of a function and an f of an argument, it should get you an f of the applied thing. So what you can do is, first of all, that's what we look in the last line, combine these two things. So f and x has type f of a comma b a, so a to b comma a. So you are tapping these two things together. And now the trick is you don't need nothing more than fmap because you only have one argument. So you need a function which takes the argument of type a to b a in a tuple and gives you back a b. And we can write this function. It's on the first line. It's just applying f of a. If you want to write it with point-free notation, that's like an carry dollar operator. But if you don't know what dollar operator is, never mind. All you have to do is apply fmap and the and. And as you can see, we are not making, we are not cheating. We are just really defining app in terms of the things which we can. And with a bit of more work, you can show that one construction is actually the inverse of the other. So you can actually go back and forth and you are not changing anything. We're not gonna do it now because we don't have the time. But the good thing is that now we can maybe see a bit easier how we get things. And I'm gonna try the fancy drawings again. So let me change the screen. Good. So okay.
While you're doing fancy drawings, we actually have a question about fancy drawings.
Good. Tell me.
Yeah, Bernd, do you want to unmute and ask your question?
Hi there. Can you understand me?
Yeah, sure.
Okay. I just get it more if I see this fancy or as the Bartos way, as there's commutative diagrams drawn. Then.
Okay, so you want me to draw commutative diagrams instead of like
more in an intuitive way the concepts. I'm not so familiar with Haskell syntax, but I have done the category for programmers, lots of chapters on it. And so if it would not to ask too much, if you can draw also like in combination with the code, these diagrams.
Yeah, maybe for pure, I could do that. I don't think I can do that from the top of my head for the rest of the diagrams, which are getting a bit bigger. So maybe what I can do maybe is try to write these things and then try to draw the categorical diagram to the side, and maybe that will help everybody which more familiar with categorical kind of commutative diagrams see this. So
That
maybe,
would be really awesome.
okay, so let me try to do this for the end. I think there was another question maybe. So before I start drawing.
No, I don't think so.
Okay, so something said like somebody raised their hand. So okay. Anyway, so again, what we have is now that okay, we have this kind of two ands. So we have the and which takes like f of a and f of b and give me f of ab, and we have the other and, so g of a, g of b, and gives me back, sorry, g of ab. So what we can do now is sort of, you know, and just to be clear, what we want to get is something which now takes a couple of f of g of a and an f of g of b, and gives me back f of g of ab. So this is getting a bit harder to read maybe, but it's like we have these nested things in a tuple, and we want to get the functor, which is now f composed with g outside and the couple inside. So what we can do, or how I like to think about it, is that what we have is something of type f of g of a and f of g of b. You know, so we start with that, and then we can apply and to this thing. So this is actually like not two arguments. It's like a tuple. So it's actually really one argument in a tuple. But okay, so we apply and what do we get? So we get you know, we get f of GA GB, because this and is sort of applied. It's the version for f. So we can take for a and b here. So this a and b are something we can choose as, at our will. So we are going to choose g of a and g of b there. So we are applying this and. And now what would be great is that we could apply this and inside of here. So if we could apply sort of this and inside of this argument, we could get g of ab, then we would sort of get f of g of ab. But we can do that. So we can pack this, and then all we want to do is to work inside of f. So if we want to get the f here, what we can do is apply f map of and. So the idea is we first apply the and, which give us, we get rid of the f inside and sort of take it outside. And then we apply f map of and, the f map to sort of go inside the f, and then the and to work with this tuple of GAGB. And that's how we get it. Let me maybe try to write a bit of commutative diagram. So what sort of you would see is that you would have like f of g of a times f of g of b, and now you're applying this and. So I'm sort of writing more categorically, like with the crosses, and then you will get f of GA times GB. And then category theories like to write the f map as the name of the functor. So you would get like f of and. And by the way, yeah, I think also if we want to be super categorical, people will actually write this like something like a cross thingy. So we can write this cross thingy here. And then if we have this, we can just get f of g of a times b. So that's essentially the kind of things that we are doing, but written in a more categorical thing. So it's right now it's all about the types, and we are just defining this. And what you can prove with a bit of time is that this actually defines a right and operation for f composed with g. I don't know if that helped, but you know, essentially I'm just trying to explain with the types how you can derive this operation. So let's get back to the slides. And this is exactly what we've been doing here. So we take the first step, step one, which is, you know, taking, applying and to F. And then the second thing is applying F map of the AND operation to this first step. So maybe the type, I just wrote the types there so you can link it to the drawings. And if you want to write it in point free form, it's sort of like you have F map of AND after AND. It's not that this will give you extra idea, I guess, that the thing on top. But look, one thing I haven't done is cheating. I'm not using app. I'm only using and F map. So I'm really creating a new applicative on this monoidal presentation out of the other two applicatives. So, you know, we've done it. And by the way, this same game we can play with many other concepts. So you have traversable. It's like map, but with effects. So instead of applying A to B, you apply A to MB, where this M can be thought as something which affects like IO or just list or maybe. And what you get is you get an FA, but now you don't get FB, you get M of FB. So if you have like, imagine you have a list of names and you want to apply like print it to the screen, which is something of type string to IO unit. You cannot use map, you need to use map M, and you will get back an IO of list of units, which you don't actually care about, but in general, you might care of with the outside. So this works perfectly fine. So as with functors, actually you get something which is traverse of traverse. So traversable functors also can be composed in this way. Alternative functors, which is an extension of applicative, which might sort of fail or have different alternatives. So you can think like maybe is something which you cannot only do a pure and get something which is okay. You can also return, you can also have nothing, which is like I failed. I don't, you know, like validation failed. And you have a way to compose different alternatives, like try this path, and if this path doesn't work, just try this other path, and that's what this kind of OR operation is doing. So this alternative thing actually it's even more magical. You know, they don't even require anything from G, so you can compose any alternative functor with any other functor. It doesn't have to be alternative. So the thing inside could be whatever, and you can still get an alternative functor, which is kind of great. And the code is here. So it's not important you understand this code for traversables and an alternative. The point is that this kind of composition works very well for a lot of things we use in Haskell. So for functors, for applicative, for alternative, for traversables, for foldables would also work. So great. Now, what happens with the grumpy monad? You know, I always think of monad being like the grumpy person who doesn't want to make friends with other monads. Like each monad is like, oh, you know, I'm so nice, I don't want to be with anybody else. So first, let me show the monoidal form of monads. So you might not recognize this like being monads. So this is like another operation called join. And this join is sort of kind of having two layers of the same functor, the same monad, like maybe of maybe, and turn it into one maybe. So, you know, this, I'm saying this is the monoidal form, and I'm going to show you later that this actually corresponds to the usual presentation with bind. But you might be asking here, you know, what is so monoidal about this definition? What's you know, monoids are always about taking two things and combining them together. What's happening here? And what you have to think is sort of switch your mind to a higher level and think not of types of values being composed, but actually of layers of Fs. So it's like you have two layers, you have F of A, and you get back one layer, which is just F of A. So that's like what is monoidal here. If you want to, you know, play the game, you can actually formalize this in Haskell. You can have a new type for what it's called for a polymorphic functions. This is called natural transformations. That's this arrow with two lines, and then join is actually be something like compose of F goes to F. You know, if you don't know what all of this means, It doesn't matter, you know, this is sort of saying, you know, this is just a way to express this phrase that the monad is a monad in the category of end of functors. That's what people say. We don't care about that so much. What we really care is that the fact that we can define monad, not with bind, but with join. And these are really the same, and I'm gonna do the same thing as I did with applicative functors. So I'm gonna define join in terms of bind. So in this case, not actually in terms of bind, but in terms of do notation, which is just binds under the hood. So I can just do this thing. So like extract from f of a, something of type f a, and then extract from this an a, and then do pure. And this will actually give me something of the right type. And what I like more, it's, you know, the fancy drawing for join, which is, you know, what's happening if we want to do bind from join. So let me show the screen again. So what we have is the join, which takes two things and turns into one. And what we want to get is a definition for bind. So bind takes a function of this type and an f of a and gets an f of b. So we can, you know, we're going to be super naive here. So we have a function, a function here, it's there, and we have something of type fa. We have something which makes this work. That's fmap. So we're going to apply fmap. You know, we have to like change the order of the arguments or whatever. But if we apply fmap to this, remember that fmap has type a to b to f of a to f of b. But now I'm going to take, instead of b, I'm going to have f of b here. So I also get f of b here. So this means that if we take these first two arguments of bind and apply fmap, what we have is f of b. But what we want is f of b. So we are going to be like the laziest people ever. We're going to say, yeah, okay, if you have a function which sort of gets you from top to bottom, then I can define it. So, you know, that's how I get join. I just want to use fmap. I can't. I need something in between. I'm going to say, you know, that's exactly what I want. Join. Voila. So it's like how you get one from the other. And that's sort of where join comes from trying to do fmap naively and then figuring out that you actually get nested f's if you apply fmap in this way. Let's go back to the slides. So that is exactly what you get. So again, we have something like I do a step one. You can think, you know, it's kind of very similar to what we've done with the other cases. We have a step one, we apply fmap naively, and then we just to join because we have too many f's around. So just this, you know, knowing that monad can be expressed as join instead of like the usual bind is going to be the key to understanding why we cannot compose monads. So I think it's a good time if somebody has a question, I can maybe answer it.
Yeah, any questions, please drop them into chat and we will answer them. I don't see any questions.
Good, so let's keep going then. So if we wanna now compose these two things, essentially what we wanna have is something which now takes two layers, but these two layers are a composition of functors. So what we have is something of, we wanna get something of this type. We have f of g, that's the first layer, which is a composition of two things, of f of g of a. So we have f of g of a, and we want to get just one layer, but this layer is now a composition of f and g. So we have f of g of a. So you know, this doesn't work because all what we can do is join two consecutive layers. So if we had like f of f, then we can do that. We have a join to do that. But now we never have two f's, one next to the other. We don't have two g's next to the other. So we are stuck. We cannot do anything here. We cannot define joins in terms of the other joins. So I always think like this is like a stupid reason, the reason is not that profound. You just find a way to define monad and see, okay, this is like another way to look at monad, but you do it in such a way that it's sort of clear that you cannot do this. So it's clear that this join is never going to work, because I cannot use, if I use fmap, I will never get outside of any f of g. I can do only things inside. If I use applicative, I'm sort of in the same situation. And the other thing I can use is maybe join. But join only works in two consecutive layers, and there are no consecutive layers here. Everything is interleaved. So yeah, so nothing's working. But just to be clear, I think there's a question there. I'm not going to show anything else with the compose, so you can write this. But
yeah, there's a question. Somebody wants to see the full code for
so
the applicative operator for the compose type.
Yeah. So I showed. I can maybe at the end show again the thing, but I'm not gonna show for the compose data type, because I said it's gonna be the same, but with compose a sprinkle here and there, which I think obscure the actual meaning. Like in this case, if we had compose, we would have like compose of compose fg of compose fg. So we would have, it's good that I can sort of use this extra screen to write stuff. So if we want to do with compose, what we would get is something which looks like compose of fg of compose fg, and we want to get from this a compose fg. And this, I think, obscures a bit what's going on, because it's not that these two compose go to get this compose together and this goes together, because you could write these four things as in many different ways of compose. You could also write compose of f of compose of g of compose of fg, and these two things are actually interchangeable. But actually, the problem is that we don't have two consecutive layers, and that's what I think the other way of looking at this makes clear. So that's why I'm not showing the compose. Good. So that's sort of it. So we cannot compose because we have interleaved layers. Reason, stupid one, but the consequences are actually quite profound, because that means that we cannot do as we were doing with functors or applicative. We cannot take any two monads and just combine them and have something which works. Maybe, I mean, we can try some fixes here and there. That's like it doesn't work like this, but we just need a small fix here and there. Maybe that's enough. So there is a fix. One fix is being able to swap two layers. So if you swap f and g, now what you can do is, you have, let's see if the screen comes. Yeah, I have f of g of f of g of a. If I swap this, I get f of g of a, and now it's great. I apply join here, so now I have one g of a, and now I apply join here, so I have one f. So now I have what I want. If I could swap in that order, so I could get a g of f into an f of g, so exactly g of f to f of g, that order. If I could swap those things, if I had that operation, then I could solve this problem. So, it would be great that we could define this operation in general. Of course, the problem is going to be that we cannot swap any two things in general. So that's not going to work. But as I said, this function does not exist in general. Some specific pairs of monads can actually be swapped. And actually, it's even harder than that. There are some cases where swap only exists in one direction. So it's not that if you can swap F and G, you can swap G and F. You actually need it on a particular direction, and this might exist in one direction, not into the other. So just to show you, and by the way, this is called in categorical terms a distributive law for the monads F and G. So that's you can, if you can swap these things, you call it a distributive law. So you can what people would say is that you can compose two monads if there is a distributive law among them. So I can show you something. So for example, there is a distributive law between maybe and any M. So you can get a maybe on the outside and any other monad in the inside and swap them. And that's the code. You can check that it actually compiles in your Haskell terminal. So that means that there is a distributive law between maybe and M in that direction. But actually you cannot do it in any other way. Try to write this function in general. It's not gonna work. So it's gonna work for some M, but there is not a distributive law between an arbitrary monad and maybe a maybe. And this also points out that order matters in sort of how we compose this kind of thing. So maybe you've seen this example before. So what I'm gonna do is take the usual meaning of the list monad as being some sort of searching in search space and returning all successes, and maybe as possible failure. Well, these two things, list of maybe A and maybe of list of A, are not the same. They do not represent the same thing. If you have the list in the outside, these are independent branches. Each of them can fail or not. Where if you have the maybe outside, it either succeeds or fails completely. And this sort of tells you that given that this kind of meaning is so different, it makes sense that sometimes you cannot even compose their meanings. You might, in this case, we could do that, but it might be the case that you cannot compose the meaning in one direction.
I have a quick question.
Yeah. That's the best question, because that's the question which just is answered in the next slide. Thank complete stranger, which this wasn't prepared or anything, of course not.
Well, just for the recording, the question is swap equivalent to sequence A?
Yeah. And that's what we're gonna see. So first of all, yes, for people which don't know what sequence A is, so there is a way, an alternative way. So you can see there are many alternative ways to do stuff for this kind of abstract idea. So there is another way. I've shown traversable as being a map with effects. So like a map in which the function you apply is not A to B, but A of I of B, of A of list of B. There is a different way to do this, which is sequence, which says that you can swap. If you now use the terminology we've been using, you can swap and take the F inside there. So for example, maybe is a traversable because you can take maybe of M of A and get M of maybe A. So that's what it tells you. So it's sort of being a traversable is similar to F has a distributive law over any applicative. So it's like this exists in one direction always. Which, by the way, it's false. There is a paper called like an investigation of the laws of traversals, which tells you that just requiring this is not enough. You actually need extra conditions on these things to actually be a valid distributive law. But okay, we are not going to know that. But yeah, there is a connection there, which is because traversable can be explained as sequence. You can think of traversable of actually having this kind of distributive law in one direction. So again, you can show that these two are the same. Maybe I'm gonna skip it because maybe we are tired of seeing things which are the same, even though it's actually very similar to what we had before. We apply something with fmap, and then we say, yeah, I was gonna swear, but I shouldn't do that on a like a public event. So we apply fmap, and suddenly we don't have what we want. We wanted m of f of v, and then we got in a step 1 f of m of b. So well, yeah, let's assume there is yet another operation which does exactly what we want, which is sequence. So that's how we get sort of this idea of sequence. I wanted to have something similar to traverse. Anyway, just to complete this idea of sequence that because it seems that there is some interest in this. Actually, for example, traversable of list is a case in which sequence can type check, but it's actually not a distributive law. And the reason for this is that this only works for a subset of monads called commutative monads, which is monads in which you can sort of do operations in different orders and the result is the same. So if you have here like A and B, maybe it's a commutative monad. It doesn't matter if you fail in any of those, then you're going to fail at the end. Otherwise, you're going to get two results. But if you think of IO is not commutative. It's not the same asking for something and printing, then printing and then asking. It's like you can see that it's different. And list is only a distributive law for monads of the first kind, for monads which are also commutative. I'm not going to go inside of this, but this is something you can see if you like look at the sort of list transformer package. You can see how easy it is to come up with a list thing which is not what you want. So what you've seen here essentially is, okay, you can take two functors, two applicatives, two whatever. You just put one after the other, and it works. You get two functors. You get a new functor. But you cannot do this with monad. This way of composing stuff does not work. So, okay, what then? We want to compose monads, and the reason, and there is a reason for this. There is this holy grail, which is we want to be able to use the operations of two monads together. So we have something like maybe, which allows us to fail, and something like a state, which gives you a way to have a state in your program. And now we want to have a program which has a state and fails. I mean, it's not so weird. We may actually want to have this, or we have IO and a state. When I keep a state and do some IO, or a read, we want to be able to compose a thing that actually makes sense. And it's a pity that we cannot just take these two things and put them together and get something with a combined sort of superpowers of each monad. So people have been thinking about this for long. There is like monad transformers is one solution, like it's coming like from the 90s, and nowadays people are talking about effects, extensible effects, algebraic effects. So let me just give me a small stroke of what of each does and why it's actually not the holy grail still. So what monad transformer do is essentially forget about this point of view of having two monads F and G and get the two monads by composition. So it's like F and G are in the same level and we want to compose. What we're going to do instead is take the G, so the thing on top, and have a wrapper around. So it's like we have an F. F is not going to be a monad itself, is going to be a transformer. And a transformer is something which you give a monad and gives you back a monad. So there is no functor composition here. So instead of compose, reader, and maybe, what we have is something like reader T of maybe. So this reader T is the transformer version. I see some other question. I'm gonna finish with these things, and then I'm gonna answer all the remaining question at the end. So that's the different view. So you don't get two things at the same level. You have like one thing, which is actually a monad, and something which wraps it to get you another monad. So it's like you put another jacket on top of it. So you can put more jackets, but a jacket is not a person. So you can think of this Friends episode of one of them like wearing a lot of things. So you have a person. So what we have with the monad was like have two people, I guess, and have a new people, which is a kind of composition of people. And now we have here is like you have a person and a jacket, and this gives you yet another person, but with a jacket and yet another jacket, and that's how you transform stuff. And actually there is almost a transformer for every single monad. So you have maybe T, which mirrors maybe, and state T, which mirrors state, and this supports the same operation. So if you can do get with reader, you can do get with reader T, and there is a library called MTL from Monad Transformer Library, which uses type class machinery to make this work uniformly. So it doesn't really matter whether you have a reader or a reader T, which is great because when you do actually writing code, suddenly you need, you have one, you thought you needed reader and a state, and actually now you need also maybe. So you just put them there and then everything keeps working because MTL magic. Now the problem is that this holy grail is not so easily attainable. So some operation can be easily combined, but when you get things with callbacks, so something like bracket, which is an operation which takes m's as inputs and gets m's as outputs and all kind of weird things. So by the way, bracket is like the resource handling operation in Haskell. So you give it like an acquire resource, how you dispose the resource, how you use the resource, and it sort of ensures that acquisition and release is done in the right way. So if you try to have this operation and combine it in several monads, it's just not going to work. So it's actually going to be quite hard. And there are some ideas to solve this. Some people say, you know, we don't actually care about composing two monads. All we care is composing with IO, because we want to have IO and then do some extra power on top of IO. And that's what the unlift IO library does. So like, we don't care about other monads. You know, we just want IO to be the important one. And then you have things, transformers on top. That's all we care about. And some others are like I kind of think like bring down the type level time. So it's like a super complicated way to make this work, and this like monad control thing. And actually they make them work, but sometimes the way it works is not what you expect. So it's kind of very surprising. It's very hard to understand what's going on. So this is complicated. And then the other part, it's algebraic effects. So let me finish this and then I'll take the questions. So the effects is first of all, I mean, talking about effects is complicated because this is research right now. There are many different proposals, but the idea is that let's not have monads being composed that have one monad, just like the F monad, usually it's called something like this. And it's parameterized by a notion of operation. So like the state monad, which is something that allows you to get and put the state, you can define it like an operation. This is like a data type which defines the operations of a state. And the thing is that because operations are defined in this kind of easy way with a data type, you can easily compose them. So kind of the trick is that you not compose monads, you compose operation and then you make them a monad out of it. And because operations are easier to compose than monads, I mean, they can be composed, this in general gives you a better way to deal with compositions. And then there is something called handlers, which state how to execute the operation. But as I said, this is richer. There are still many different proposals. People are still thinking what is the right way to encode these things in Haskell, and in general, how to think about this. So, I mean, the idea itself comes from very old, from the 70s, from a guy called Plotkin doing this, I think, and then but has been revived in the last 10 years by research in Haskell. Yeah, let me take some questions now. First of all, I see some things are yeah, there is a typo there. So there is, yeah, it's a research area. That's what this is Richard R. I mean, it's very research. So, you know,
this is why you have editors.
Yeah.
Yeah, Bernd has another question.
Yeah, so I see here, so it's commutative in this example because multiplication is distributive over addition, but not vice versa. So that's we were talking about this sort of commutative things, isn't it? So, okay, how I think about it is that your usual, at least my usual intuition of what distributive and commutative mean in this kind of categorical thing doesn't really, are not really tied to, you know, the usual commutativity and distributivity we have here. So I had very long rants saying, you know, why people call this a distributive thing. I mean, everything what it's doing is sort of commuting stuff. So this should be a commutative law, not a distributive law. But on the other hand, it's sort of distributing the F's over the G's. So it's like what plus and times do. So you can call it this way. So I would really, you know, I would really sort of say that, at least for me, the safest is that, yeah, sometimes these kind of things are so general and so abstract that you can see them in many different ways, and they are tied to distributivity in some way, which might not be clear or might be super clear to you. So,
and yeah, there's another question from
there was
KK. Do you want to unmute and ask your question?
I can read it otherwise.
Read it, right? It's Yeah, do you have a favorite algebraic effects library? What do you think of polysemy, for example?
Yeah, so yeah, to be honest, I haven't used polysemy that much to be able to say too much about it. So I actually from what I've been doing, transformers have worked well for me all these years. And one good thing if you use monad transformers is that actually GHC is able to optimize your code and to so you actually are not paying a price to have this abstraction, whether for things like polysemy and other algebraic effects. This is not true yet, so people are working on this, but this is, so that's sort of the main reason for me to doing this. If I want to have code which runs, which is fast, just not slower because I'm using a specific library, then transformers is your choice. Yeah, but I actually don't have a favorite. I I remember seeing like PureScript used to have like in this F library, and I thought this to be quite nice. But yeah, in general, I think there is so much flux that having like a favorite one right now, it's some kind of difficult. But yeah, indeed, I mean, if you think of, if I should recommend one, I should recommend polysemy because it's like the best maintained one.
Fun fact, I shared an Airbnb for ZuriHack one year with the author of Polysemy, Sandy McGuire. Maybe I should ask him to do a talk for us as well.
I mean, monad transformer versus polysemy would be a great thing. Like,
oh, maybe I should set up a debate.
Huh?
Maybe I should set up a debate.
Yeah, that's
classic. It's a very classic debate. Do you have more to show before we go to final questions? I think.
Yeah, I saw there is another question.
Is there?
Yeah, but it says it's private, so maybe I can read it out loud. So
okay, sure. I didn't see it.
Yeah. Yeah, so it says something like monad transformation is so hard. What about lenses? So actually, I mean, this kind of things don't actually have a relation like lenses and monads. So you can find a relation. So of course there is a relation, and the way you implement lenses, sometimes you're using this kind of complicated kind of abstractions, and I've seen people doing like lenses for monads. So like a lens is going inside a layer, but I don't think there is, at least for the topic of this talk, there is not much this. So yeah, that's sort of yeah. If you give me 1 minute, like the advertisements from the people who actually let me do this, well, I'm doing stuff. So if you like this kind of talks at 47 degrees where I work, we are gonna soon announce that we wanna, do more talks and have like our own things to talk. So maybe, sorry, Steve, I know you're running a meetup, but we wanna run our some talks. And the idea is that we wanna bring, like functional programming all together. So not have Haskell or Scala or whatever, like have talks and webinars and courses about all kind of functional programming. So, I mean, details are gonna follow in a few weeks. So if you like this kind of, learning about functional programming stuff, and maybe in the language you're actually using in your daily life, not in Haskell, which is something which not many people use daily, you can keep it tuned. So just, let me give a brief summary of everything just to have a closure. So, functor composition works very well. We did it for applicative alternatives, traversables, but we cannot do this in general for monads. And the reason is that, this join operation just, we cannot define it because we need to swap, the join puts two F or two Gs together, and now you have interleaving. And some pair of monads worked okay. This is called having a distributive law, but because it doesn't work in general, we have monad transformers, we have effects trying to solve this. So, that's it. Thanks for listening. If there are any other questions, and of course, feel free to ping me on whatever social media except for Facebook, where I'm not just pygmy, and we can chat about any other thing about it.
So Paul has a question if he would like to unmute.
Hi, Alejandro. Thanks for a great talk. So just a quick question on like the order of composition. So maybe some intuition on like, okay, I want to do this and that. So what would be the right order when it comes to both like functor composition and also monad composition or effect composition?
Okay, so I have to say this is something which actually depends heavily on the concrete example. So it's this kind of things where you cannot actually have a general thing. This depends, you know, if we have list and maybe, this depends on being list and maybes. But kind of a general idea that you or something which I use, that there are some functors, some monads, applicatives, which can sort of be sprinkled anywhere. So a reader, which is just a way to have an extra context, can sort of be put anywhere. It doesn't matter, because it doesn't matter. You are going to just use the context and you have to provide it here or there. But for sort of what people sometimes call control monads, things which sort of branch the computation or fail. So essentially for things like list or things like maybe and either, which fail, you have to be very careful. So what you would see is, what most people do is kind of, well, if you want to have IO, you usually put it at the bottom, because you don't have an IO transformer. Then you think carefully about your extra layers with maybe and either, and then you stack on top the things which don't really matter on the order. So like readers and writers and kind of this kind of thing. So, but yeah, unfortunately, apart from that, I cannot give you a more insight. It's so dependent on the functor monad you choose in every case.
Thank you very much. And do I understand correctly that this order matters equally whether you compose things just using the functor composition, or whether you use like monad transformers? Or
yeah, it's actually you know, I just sort of I brought this from the fact that you can define swapping one order and not the other, but indeed even for functors there is, you know, the reading of list of maybe different from maybe of list is actually different in both cases. Is that you know, it's kind of tricky, but sometimes because you fmap and app sort of work more independently, it's harder to that this bites you. But yeah, I mean, because you at the end of the day you're mostly going to use monads and not just only functor alternative. This is actually gonna, you know, this is gonna be something you have to think about even for if you use fmap.
So we have a question from Ulrich. So Ulrich, do you want to unmute?
Yeah, here. Sorry, I unmuted myself.
Hi, welcome.
Yeah, thanks for the talk. I'm sort of a newcomer, but I've been struggling with Haskell and functional for quite a while by now, with a background just to write not simple, but applications, not from a research perspective, but just for like working software. And I have the feeling it's very hard if you come from the outside to actually pick the right set of libraries, or even, as you just said, monad stacks that simply work. And I was asking if there is some sort of best practice, like in the Java world, you either pick Spring or you pick J2EE and the thing just works. And you don't have to think about, how do I set up my dependency injection container, and which logging framework do I use, and this and that. And here, for a newcomer, I find it super difficult to wrap your head around it. And there's lots of people saying, yeah, but you don't need to understand it. I have the feeling you do need to, because otherwise you cannot write any serious applications.
Okay, so maybe I can sort of answer the concrete and the general. So what's my point of view of how you can approach this kind of thing? So if you want to write stuff, my recommendation is, you know, stick with monad transformer, the MTL library, and thing which builds on top of it. so you have like, there is a bunch of small libraries like Monad Logger, which is like a login facility as a monad transformer, or Resource T, which is a resource management monad transformer. So if you know those, and these are, you can usually see that they have like a lot of downloads in Hackage. So they are kind of that they are used by many applications because people download it as a dependency. Then you are happy. And as I said, I mean, I do Haskell in my daily job, and all I use is monad transformers. And sometimes I go for some kind of very specific libraries into one of these Unlift. I usually use Unlift.io because indeed I agree with the writer of Unlift.io. I never want to do complicated stuff unless I'm doing IO. So I only want to wrap things with IO. So I found that MTL, so like the now almost old MTL library, and things which built on top of it with a sprinkle on Lift.io works well for everything. Now for the most general thing, I mean, that's something I see people struggling with coming to Haskell, because you have the problem that you have like the forums and the kind of books which are starting to come now, like books about how you write Haskell. But then there is like the academic literature, and there is a lot of academic literature, and I don't think that you should not understand it. So I do not agree with people which say you don't need to understand monad transformer. Well, you need to understand the problems and why it comes. What you don't need to understand is the paper which introduced the concept in 1990s using another terminology and academic lingo. What we should do as a community is actually be able to write new material which is more approachable to people which are coming, and sort of do this kind of things. So, I mean, I try to do my little bit, but nowadays you can see there is like books either published or coming for different levels. So I think that this already distilled much of the knowledge. But yeah, I mean, I don't think there is nothing like Spring where you say this is my set of libraries that you should use. That just do not exist. So sociologists can try to figure out why Haskell community is so reluctant to say, yeah, this is the good one, or this has this mark as this works. Everybody's so reluctant to do this, whereas in the Java world, people just say, well, this is something we know it works, and we're gonna stick with it even if it's not the perfect solution. But yeah, this is not how Haskell community works.
Alejandro, someone asked if you're going to be making the slides available.
I can do that, yeah.
Okay, so yeah, if you send me a link, then I will post it.
Yeah.
It looks like Bernd has another question.
Yes, to get a bit better intuition about it, have you used product types and sum types in your examples, and so the product types distributes over the sum types?
But what should I show the relation? I mean, this is indeed true, but I don't see the
they are not commutative anymore, because it's similar to multiplication and addition. Yeah,
that happens. Actually, I think in types both distribute over the other, so they are like, or no, I mean, no, only one distribute over the other. So they are, I mean, product types and sum types, they actually have a good name, and one distributes over the other. And that there is another thing called a distributive operation when you talk about this kind of, if you think of this categorically. But what I was mentioning is just the distributive law being this kind of thing with this type. I mean, to me, the name doesn't give that intuition, because you can also think about being a commutation between F and G in the sort of sense of swapping. But I mean, what you're saying is true. But I think, and if you do composition in this way, but this is going to be a different kind of distribution that the distributive law I was talking about the monads.
Okay.
Yeah. And KK has another question about Unlift.io.
should I write it myself, read it myself, or?
Yeah, can you just say a bit about why it's useful? I mean, you mentioned it, but I haven't used it.
Yeah, so okay, that's the thing. So when you, many of the Haskell code you end up writing is essentially IO as a monad. So you need to do database operations or network or whatever, and then you stack some transformers on top. So you may have a reader T, which is kind of way to inject information to keep your configuration, or at the same time you have some state T of S. So in practice, you end up with transformers on top of the IO monad. The IO monad is required to do like side effect operations. Now, the problem is that when you use the Haskell prelude, everything is for IO, just IO. So if I want to print to the screen, I cannot do this because I am not in IO. I am in IO where some transformation has been applied. So I am in reader TR of IO. And so the prelude essentially stops working. So what you need is like something which generalizes all the operations in the prelude, everything which works in IO, to actually be able to use this in this more generic context. And you know, maybe you think you don't need IO that much, but for example, in Haskell, if you want to do concurrent programming, you are more or less stuck in IO. So that's the only way where you can start a new thread. So this comes quite often, and you may want to do this. And as I said, you cannot do this because everything in the base library is for IO, and then lift IO is it's one way to do this in general, but it also comes, and that's what I find the most useful, comes with just somebody took the time to go over every single operation that you may want to use in IO and generalizing it, you know, one by one. You only need to write like one extra line for each of them, but somebody took the time, and this is something you end up using quite often, at least in the kind of applications I write.
Okay, are there any final questions or comments that anybody would like to make? We've got lots of compliments, which is nice to see. For both of us, you know, thank you very much for the appreciation for the talks and for each individual speaker. It's always fun to just see people, you know. I know lots of people in the FP world. I don't get to see them very often, and this has been a great way to reconnect. One final question for me, Alejandro, what are you working on now?
Okay, so right now I'm sort of working in 2 projects. So I'm working on this kind of training things that we are unveiling. So that kind of things that we like to say talks tailored with love. So we're trying to kind of have talks which sort of bring different sides of the FP community together and see, you know, all angles. And apart from that, there is a library I've been working on. It's called Mu Haskell, and that's a library to do microservices. It's a library to do gRPC and GraphQL microservices. That's like
that's your thing, the GraphQL thing. Okay.
Yeah, one of the GraphQL things, and this is like it's been very fun because what we kind of do is, you know, in GraphQL or in gRPC, you already have the schemas. So at compile time, these schemas get translated to a very complicated type level Haskell code, and we can use this code directly to check that what you've written is okay or not. So you have like type safe, microservices, servers or clients, but you don't actually need to write the Haskell types. This is coming from your gRPC or protocol buffers or Abro definitions. So we are, you know, coming from that, we are trying to expand and, you know, be able to connect with like Kafka using the Abro thing or with all kind of things. So that's actually where I am always using this kind of stacks with IO, because it's all about at the end putting something on the wire or, you know, bringing something from the wire. And it's been really fun because I get to use like all the things I usually claim that are useful. Well, I've actually, you know, have a big thing where it's useful.
So you started this project, or you're just working on it?
Now we've done 3 releases now, so that there is some video of some talk I did like last month in the Amsterdam virtual meetup about this. So this is sort of like 0.3 release, so it's not like production ready, mostly because nobody still wants to bring the things in production in Haskell if they don't control everything. So it's mostly toy examples and ourselves using it internally. So I don't want to say it's production ready, but it's like feature complete from what we wanted to do. So be able to have like all this kind of microservices in a unified language.
Okay, well, you've given me a great segue because Flavio, who I guess you work with, Flavio Corpa,
Yeah.
he's asked if he can do a short talk on Mu at some point. I was trying to convince him to do a full-length, longer talk. Maybe you can convince him. But the segue is I'm looking for people to do shorter talks. I know not everybody wants to do a 1 hour long presentation. So if anybody in the Berlin Functional Programming Group community would like to do a 10-minute talk, a 20-minute talk, I can group a few of these together and we can have an evening of shorter talks and discussion. And I guess Flavio will be part of that at some point. Let's also thank Alejandro for joining us and thank him for his time and show some appreciation. You can wave your hands, you can do a clapping emoji. And thanks again, Alejandro, for joining us virtually in Berlin.
Yeah, it's a great thing. I mean, I'm hoping we can soon meet and have a beer in person instead of like having to virtually see all the walls of our houses. But
yeah, definitely, you're coming to Berlin and your first beer is on me.